This video is on section 8.1, which is basic integration rules, and it's really just a review of integration. So if we look at this first example, we've got x squared and 9 on the bottom. They're both perfect squares. If you pull out the 4, which is a constant, you're left with this here, which is one of the inverse trig functions, where a is the number. So a would be 3, and u is your variable, which is x squared, goes back to u being equal to x. And since it's x squared plus 9, then that's the same as the inverse trig function. So really you have 4 times 1 over a, which is 3 in this case, tan inverse of u over a plus c. On this example, it looks similar to the last one we just did. However, now we've got 4x on the top, which is going to change our solution from being an inverse trig function into, we're going to do u substitution. So u will equal to x squared plus 9. Our du is 2x dx. And what we'll do is we'll divide by 2, because we've got x dx on the top and we're going to pull out the 4 anyways. So we'll have 4 integral of 1 over u times du over 2. Pull out your constant. So you have 4 over 2, 1 over u du, which simplifies to 2. The integral of 1 over u is ln of u, which in this case is x squared plus 9, and then plus c. On this example, now we have 4x squared on the top, and our degrees are matching up here, so what we're going to do is we're going to use long division to simplify it. So we'll have this. We want 4x squared, we have an x squared, so we're going to multiply by 4. That'll give us the 4x squared plus 36, but we're going to subtract this, so these cancel and we're left with a negative 36. We can't do anything else, so that's a remainder. So we rewrite this to be the integral of 4 minus 36 over x squared plus 9 dx. If we integrate 4, then that just becomes 4x. This portion here is similar to our very first example that we did. Pull out the 36, you're left with 1 over x squared plus 9, which again is an inverse trig function when you integrate it. So that becomes minus 36 times 1 over the a, which is the square root of 9, tan inverse of a, which is the square root of x squared, which is x, over a plus c. Looking at this example, it seems kind of difficult to know where to start. So what we can do is we've got a plus sign in our numerator, so we can split it up into 2 integrals. It'll go the integral from 0 to 1 of x over square root of 4 minus x squared plus 3 over the square root of 4 minus x squared dx. So for the first one, we're going to use u substitution, u being the 4 minus x squared, du would be negative 2x dx, divide by negative 2, divide by negative 2. So we get the integral of 1, let me rewrite that. U to the negative half times du over negative 2. For this one here, pull out the constant, And then we've got 1 over the square root of the difference of squares. So our a squared will be 4, making our a2. And we've got u squared to be x squared, so then u is equal to x. This is also an inverse trig function, but it's not tan inverse. This time it'll be sine inverse. So that'll be plus 3 the integral of 1 over square root of 4 minus x squared dx. So for the first part, when we pull out the constant, which would be negative half integral of u to the negative half from 0 to 1, we end up with negative 4 minus x squared to the half. And then when we do this portion here, we put plus 3 sine inverse of u over a. And don't forget we have to evaluate this from 0 to 1, which would give us an approximation of 1.839. For this example, it's kind of like our previous example. So what we're going to do here, if you notice here, 16 is a perfect square, and you can rewrite x to the 6 to be some form of a perfect square, which we can actually rewrite as x cubed to the squared power. By doing so, that gives us the difference of squares per se, where a squared is your 16, you simplify that to be a being 4, and your u squared is x to the 6. If you take the square root of that, then that'll just give you x to the 3rd. Now if we take the derivative of u, that gives us 3x squared dx. In our numerator, we've got the x squared portion, so we need to divide by 3. When we rewrite this, we'll end up with 1 over the square root of a squared minus u squared times du over 3. Pull out your constant, integral of 1 over the square root of a squared minus u squared. That's also an inverse trig function, so you end up with 1/3 sine inverse of u over a plus c. For this next example, we can't use u substitution, we can't use long division, we can't, any of the integration rules that we've learned before aren't really going to help us solve this integral. But what we can do is we can add or subtract terms to the numerator so that we can separate it into 2 fractions, which will make it easier for us to integrate. It would be best if we add and subtract e to the x on our numerator. So we have 1 plus e to the x minus e to the x. By doing so, we're not changing the function, we're just adding extra terms so that it'll help us integrate it. And the bottom stays exactly the same. Well, if we split it up into 2 fractions now, you'll have the integral of 1 plus e to the x over 1 plus e to the x minus e to the x over 1 plus e to the x dx. The reason we split it up in this manner, we know that this part will simplify to 1 minus, here we can do u substitution, 1 plus e to the x. Our derivative of this is just e to the x dx, which is already part of our function. When we rewrite it, it would then be 1 over u du, and now we could integrate it. But we'll integrate it in terms of x. So the integral of 1 will be x minus 1 over u is ln of u, but u in this case is 1 plus e to the x plus c. If you look at